Krishnan. Today, our new chapter is elasticity. Elasticity, or we can write this chapter as mechanical properties of solid. Mechanical properties of solids. Okay. Firstly, I will give you a short revision about the topic. Then I will discuss what are the previous year question of that topic. Okay. Now, firstly, considered a body which is known as a rigid body. Rigid body are those body in which the intermolecular space between two bodies, intermolecular distance between two fixed two point is fixed. Suppose this is the point A, this is point is B. So this will be a intermolecular distance between them. If we apply any deforming force, topic is here deforming force. If we apply any deforming force means a force which can change the shape and size of an object. So rigid body are those body, if we apply any deforming force from any side of it, the distance between two intermolecular point does not change. This type of body is known as a rigid body. But there are two another types of body which is known as the elastic body and plastic body. First, a body is like that. Suppose there are two intermolecular points A and B. The distance between these points are D. Now, if we apply a deforming force on it, so on applying deforming force, the distance between these two points can be changed. But after removing the deforming force, they regain its original shape and size. So these are so this body is known as the elastic body. Means a body in which we apply a deforming force, the distance between two intermolecular points can be changed. After removing the deforming force, they can regain its original size. So this type of body is known as the elastic body. Now, second is plastic body. Plastic body are those body in which if we apply the deforming force, the distance between two intermolecular point changed, but after removing the deforming force, they did not came into original shape and size. So this type of body is known as a plastic body. So firstly, we have discussed about the rigid body. Rigid body are those body in which the distance between two intermolecular point cannot be changed after applying any deforming force. And next we have discussed about the elastic body. Elastic body are those body in which we apply deforming force. The distance between two intermolecular point can be changed. But after removing the deforming force, they regain its original shape and size. So this type of body is known as the elastic body, and plastic bodies are those body in which we apply a deforming force. The distance between two intermolecular point can be changed, but after removing the deforming force, they cannot regain its original shape and size. This is known as the plastic body. Okay, so elastic body is clear. Plastic body is clear. Perfectly elastic body. One topic is perfectly elastic body. Perfectly elastic body is that body. Suppose there are two type of body. Let's take by example. There are two body. The intermolecular point are A and P. The distance between them are T. Both are elastic body, but which is perfectly elastic and which is only elastic. Suppose the point between second body is P and Q. Now consider the condition. If we apply deforming force on it, okay, so what happened when we apply deforming force, the intermolecular distance between them is changed. Now when we remove the deforming force, what will happen? So After removing the deforming force, it regains its original size. Maybe I can say that it will become in 1 second. Consider second body in which I apply a deforming force. On applying deforming force, the distance between P and Q, that means intermolecular point between intermolecular point inside them changes. But after removing the deforming force, they regain its original size. But it can regain in 0.001 second. So when we apply a deforming force, the body immediately regain its original shape and size. So this type of body is known as the perfectly elastic body. Okay. So perfectly elastic body is if a body regains its original size and shape immediately after the removal of of deforming force, then it is said to be perfectly elastic body. Okay, so this is the example of perfectly elastic body. Just a minute. Okay, so perfectly elastic body is if a body regains its original shape and size immediately after the removal of deforming force, then it is known as the perfectly elastic body. Now, second topic is perfectly plastic body. Perfectly plastic body. Now, second one is perfectly plastic body. So consider two type of body. Both are plastic body, but what happened in this? Suppose the intermolecular distance between these points are A and P. The two intermolecular points are A and B, and the distance between them is D. Now, the second body, the 2 points are P and Q, and intermolecular distance between them is D. Now, if we apply a deforming force, if we stress this body, so what will happen? The distance will increases. That means they change the distance between two intermolecular point can be changed. After removal of deforming force, what will happen? So, when we remove a deforming force, so suppose this is a elongation is D. After removing deforming force, they show a small tendency to regain, but they cannot come in their original shape. Suppose this is their original D, but they cannot come in their original shape. D is their original condition. If we stress to D dash after removal, after applying the deforming force, we stress to D dash. After removing the deforming force, what will happen? It shows some tendency. That means it will come at a D double dash, but it cannot come at a D. So this is known as a plastic body, which means which can show us some amount, small amount of a small tendency to contract. Okay, a small tendency to come at a original position. This is known as a perfectly plastic body. Sorry, plastic body. So in perfectly plastic body, what will happen? Suppose this is D. If we stretch body to D dash on applying the deforming force, after removal of deforming force, it cannot show any tendency to regain its original shape is known as the perfectly plastic body. Okay. So a body which cannot show any tendency to regain its original size after removal, the original shape and size after removal, the deforming force, then it is said to be a plastic body. And this property is known as the plasticity. If a body does not regain, if a body does not regain its original size or shape. If a body does not regain its original size or shape, even after the removal of deforming force, even after the removal of deforming force, even after the removal of deforming force, it is said to be plastic body. It is said to be plastic body. Sorry, it is said to be uh, if a body does not regain its original shape. Or plastic body. Okay, this is a definition of plastic body. But what is a perfectly plastic body? Perfectly plastic body is if a body does not show any tendency. If a body does not show any tendency to regain its original size and shape, size and shape after the removal of deforming force, it is said to be perfectly plastic. It is said to be perfectly, perfectly plastic body. So clear what are elastic body, what are plastic body, and what are perfectly plastic body. Now, one topic is came here, stress. So what is the stress? Stress is defined as the force applied per unit area. Simply, stress is defined as the force applied per unit area. SI unit of stress is Newton per meter square. So this is known as the stress. Stress is simply the force applied per unit area. In stress, you will see about so its SI unit is Newton per meter square. CGS unit is dyne per centimeter square. Dyne per centimeter square, and dimensional formula is ml minus 1 t minus 2. Now stress have four types. There are four type of stress. First is tensile stress. Tensile stress. Second one is compressible stress. Compressible stress. Third one is hydrostatic stress. Hydrostatic stress. And fourth one is tangential stress. Tangential stress. Tangential stress. Now, tensile stress is defined as suppose this is a rod of length L. Okay, this is a unit cross sectional area A. If we apply the force, so the length of the body will increases to L plus delta L. So this type of force is known as tensile. This type of stress is known as the tensile stress. That means on applying the force on a unit area, there is an increase in its length. So this type of force, this type of stress is known as the tensile stress. So what is tensile stress? The it is the restoring force. It is the restoring force set up per unit area, set up per unit cross sectional area of a body, set up per unit cross sectional area of body when the length of body increases, when the length of a body increases in the direction of deforming force, in the direction of deforming force, in the direction of deforming force. Okay. This is tensile stress. This stress is also known as longitudinal stress. So tensile stress is also known as longitudinal stress. This stress is known as longitudinal stress. Now, second is our compressible stress. So compressible stress means, suppose this is the rod of length L. If we apply a force on its unit cross-sectional area, what will happen? Its length will decrease. If we apply a force, if I compress the rod, so its length will be decreases by delta L. So this is its new length, and this is its original length. So when we applied a force on unit area or we compress a body, then the length of a body decreases in the direction of deforming force. This is known as the compressible stress. So it is the restoring force. It is the restoring force set up per unit area, set up per unit cross sectional area of body, cross sectional area of body when its length decreases, when its length decreases under a deforming force, under a deforming force. Okay. When the length of the body is decreases on applying the deforming force, this is known as the compressible stress. Now, next is hydrostatic stress. So, what is hydrostatic stress? Consider a body of volume V. Now, suppose this is a body of volume V. If I apply force from all four directions, so what will happen? Its volume will decreases to delta V. So when we apply a force on unit area of each side of a body having volume V, so there will be a decrease in volume V. So this is known as the hydrostatic stress. So the definition of hydrostatic stress is if a body is subjected, if a body is subjected to a uniform force from all sides, then the corresponding stress, then the corresponding stress is known as hydrostatic stress, is known as hydrostatic stress. Hydrostatic stress. Last one is tangential stress. Tangential stress. Fourth one is tangential stress. So what is tangential stress? Suppose this is the body which is fixed on a plane. On applying force on a body, what will happen? It will, this part is fixed, the AB length of a body is fixed. So what will happen if we apply a body tangentially to it? So it will deform at an angle theta. So this type of stress is known as the tangential stress. So when a force acts tangentially, when a force acts tangentially to the surface of a body, to the surface of a body, it produces a change in shape of a body. It produces a change in shape of a body. It produces in change a change in shape of a body. The tangential force, the tangential force applied per unit area, applied per unit area is equal to tangential stress. Is equal to tangential stress. So all type of stress is clear. Now next is strain. Next topic is strain. So what is a strain? Strain is change in dimension upon original dimension. Change in dimension upon original dimension. Change in dimension upon original dimension is known as strain. Original dimension. Suppose this is the body of length L. If I applied a force on it, so what will happen? Its length will be increases. So how much there will be a change in its dimension? Suppose L plus delta L. So how much change will be there? Delta L. L plus delta L is its whole length. So what is change in its dimension? Delta N, what is its original length L? Suppose the value of L is 5 and L plus delta L is 8. So delta L value will be 3, 5 meter, 8 meter. So delta L value will be 3 meter. So its unit will be, now I am taking example that if L is equal to 5 meter and L plus delta L is equal to 8 meter, so delta L equal to 3 meter. So 3 meter upon 5 meter. Meter is cancelled by meter. So what it means that it will be a unitless quantity. Okay. So it will be a unitless, and if it does not have unit, so it is also known as dimensionless quantity. It is unitless and dimensionless quantity. So there are three type of strain. In strain, we have to discuss three type of strain. First is longitudinal strain. Longitudinal strain. Second is volumetric strain, and last one is shear strain. First is longitudinal strain. Now, taking an example, suppose this is the body of length L. If we apply a force on this body, so what will happen? The length of the body will be increases by delta L. So the length of the body will be increases by delta L. So what is longitudinal strain? The change in length upon original length. Change in length upon original length. You can write the definition that it is defined as the change in it is defined as the ratio of change in length upon original length. Okay. So how much there will be a change in or change in length? First there is L. Now the value of length will be L plus delta. So change in length is delta L and original length is L. So this is known as the longitudinal strain. Second is volumetric strain. Now consider a body which have volume V. Suppose this is the body of volume V. If I apply force from all direction, now what will happen? Its volume will be changed. Its volume will become V minus delta V. Okay. So how much, what is the volumetric strain? Change in volume upon original volume. Change in volume upon original volume. So what is change in volume here? The change in volume is V minus delta V, final volume minus initial volume. So V is cut by V. So change in volume is minus delta V upon V. So this is known as the volumetric strain. Now, shear strain. Last one is shear strain. Now consider a condition if a body have fixed side AB. Now, if I apply a force on body from rightward. So what will happen? This line, this part AB is fixed. So it will move at that angle theta. So what is shear strain? Relative displacement between two parallel planes, two parallel planes upon distance between parallel planes. Distance between parallel planes. Parallel planes, which is equal to theta. Okay, so this is shear strain. Now we have discussed all type of strain. One thing is here compressibility. Okay. Now next topic is Hooke's law. Now what this Hooke's law tell us that within the elastic limit, within the elastic limit, the stress is proportional to strain. The stress is proportional to strain. The stress is proportional to strain. So Hooke's law defined as that stress is directly proportional to strain, or if we remove the sign of proportionality, a constant is came which is known as the modulus of elasticity. So E is equal to stress upon strain. What is E here? E is modulus of elasticity. This is defined as the modulus of elasticity. Now, what is the modulus of elasticity? It is the ratio of stress and strain. Its SI unit will be same as the unit of stress, because strain does not have and does not contain any unit. So the SI unit of modulus of elasticity is same as the modulus or same as the stress, Newton per meter square. Or dimensional formula is also same. ml minus 1 t minus 2. CGS unit will also same as stress, which is equal to dyne per centimeter square. So remember one thing, that if any modulus of elasticity will came, so you have to write all modulus of elasticity have same unit, Newton per meter square. Now, next is types of Hooke's law. In this, we have discussed about types of modulus of elasticity. So there are three types of modulus of elasticity. First is Young's modulus of elasticity. Young's modulus of elasticity. Second one is bulk modulus of elasticity. It is denoted by Y. Bulk modulus of elasticity. It is denoted by K. And last one is shear modulus. Shear modulus or modulus of rigidity. Modulus of rigidity, or the name of this one is modulus of elasticity of shape. Modulus of elasticity of shape. Now, first one is Young's modulus of elasticity. Young's modulus of elasticity. Young's modulus of elasticity. So Young's modulus of elasticity defined as the within the elastic limit, the ratio of longitudinal stress to the longitudinal strain is called the Young's modulus of elasticity. That within the elastic limit, within the elastic limit, the ratio of the ratio of longitudinal the ratio of longitudinal stress to the longitudinal strain to the longitudinal strain is known as Young's modulus. It's known as Young's modulus of elasticity. Okay, it is denoted by Y. Y is longitudinal stress upon longitudinal strain. Longitudinal stress upon longitudinal strain. So the value of longitudinal stress is force upon area, because all stress are same. They are force upon area. Okay. Now taking an example, suppose this is the body of length L having area A. If I apply the force, so the length of a body will increases by L plus delta L. L plus delta L. So value of this is F upon A by delta L by L. So Y is equal to F upon A times of L upon delta L. SI unit is same, Newton per meter square, and dimensional formula is same. Okay. All modulus of velocity have same SI unit, Newton per meter square, same CGS unit, dyne per centimeter square, or same modulus, same dimensional formula, ml minus 1 t minus 2. Now second one is bulk modulus. Bulk modulus of elasticity. It is denoted by K. So what is bulk modulus of elasticity? Suppose a body have volume V. If I apply force from all sides, so what will happen? Its volume will be decreases by V minus delta V. So the bulk modulus of elasticity is defined as the ratio of normal stress to the volumetric strain. So bulk modulus is defined as a within the elastic limit, the normal stress upon volumetric strain. Volumetric strain. Normal stress, or you can say that the hydrostatic stress. Okay. So the all stress have same value up upon A, and volumetric strain is minus delta V upon V. We have discussed in the previous slide about that. So minus F upon A into V upon delta V will be the formula of K. Same, they also have the same unit Newton per meter square, same CGS unit dyne per centimeter square, or same dimensional formula ml minus 1 t minus 2. Now next is bulk modulus of elasticity is done. Now last one is modulus of rigidity or shear modulus. Modulus of rigidity or shear modulus. So what is this? The within the modulus rigidity or shear modulus is within the elastic limit, the ratio of tangential stress, the ratio of tangential stress to shear strain, to shear strain. Now, if a body have fixed surface, one of the fixed surface AB. Now, what happen if I apply a force on any of its length? So it will bend toward like that. So shear modulus is defined by eta. Eta. Eta is defined as tangential stress upon shear strain. Shear strain. So tangential stress is F upon A and shear strain is theta. So this is defined as the modulus rigidity, same SI unit, same dimensional formula. Now one more topic is here, compressibility. 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 Compressibility is defined as the bulk upon bulk modulus of elasticity. Is defined as the reciprocal of bulk modulus of elasticity. Bulk modulus of elasticity. So the value of compressibility will be 1 upon K, or you can write it as by minus A delta V upon FV. SI unit is inverse of bulk modulus of elasticity per Newton meter square. Dimensional formula is M minus 1 LT minus LT2. So that are compressibility. Now next topic is here Poisson ratios. The next topic is here. Poison. Poison ratio. Now, what is this ratio defined as? Defined as. Suppose this is the body having length L and diameter D. Having length L and diameter D. On applying the force, what will happen? The length of the body will increases to delta L. The length of the body will increases to delta L. But on elongation, there will be a decrease in its diameter. Now, on applying the force, the value will be L plus delta L, and the value of the diameter will be D minus delta D. So, Poisson ratio is denoted by sigma, and it is defined as the ratio of lateral strain to longitudinal strain. Lateral strain is change in its diameter upon original diameter, and longitudinal strain is change in length upon its original length. So minus delta D upon D, and L upon delta L, change in length upon original length. So its value will be minus L upon D into delta D upon delta L. Okay, negative sign indicate that the longitudinal strain and lateral strain are in opposite direction. It have no units, no dimension, no dimensions. Okay. So these are the values. It is left. Last is your the last topic of this chapter is elastic potential energy. After that, I will discuss important question which had come in your previous year. Elastic potential energy. Elastic potential energy. So elastic potential energy. The work done in stretching the wire. The work done in stretching the wire is stored in it as its elastic potential energy. Elastic potential energy. Okay. Okay, just wait on. So now see the proof of it. This is also come in your previous year after no, in maybe 2 or 3 times. Okay. So expression for it is suppose a wire, suppose a force F, expression. Suppose a force F applied on a wire. Suppose a force F applied on a wire of length L increases its length by delta L. Its length by delta L. Initially, the internal restoring force on the wire is zero. Restoring force on the wire is zero. on the wire is 0. When the length, when the length is increased by delta L, when the length is increased by delta L, the internal force from 0 to F, the internal force increases from 0 to F, 0 to F. Now suppose this is the body having its initial length L. At initial, the force restoring force is 0. On applying the force F, what will happen? There will be an increase in its length. On applying force, there will be an increase in its length. So the restoring force will be average restoring force will be sum of force upon total number of force. So first force is 0, second force is F, and there are two quantities. So the value of force will be F upon 2. Now on the wire is work done on the wire is force into displacement. The formula of work done is force into displacement now. So work done on the wire is equal to force into the displacement. And what is the displacement here? The displacement is increase in its length L from delta L. So the displacement will be here is delta L. So the work done is stored as, and instead of force we write as average force. So force into increase in its length. This work done is stored in the form of internal energy or elastic potential energy. This work done is stored in the form of elastic potential energy, elastic potential energy. So U is equal to W equal to 1 upon 2 F into delta L. Okay. Now U is equal to 1 upon 2 F into delta L. Now multiply and divide by A. I am multiplying and divide by A. And now I'm multiplying and dividing it by L. So the value will become U into area into length is volume. So half into F upon A is stress, and change in length upon original length is strain, into area into length is volume. And if it volume come on a by of U, so energy per unit volume is defined as half into stress into strain. So elastic potential energy per unit volume. Elastic potential energy per unit volume. Potential energy per unit volume. Per unit volume defined by small u, which is equal to u upon v. So small u equal to half of stress into strain. Okay, clear? So this is the value of elastic potential energy, which is equal to half of stress into strain. Now I am discussing about the previous year questions of your Telangana. Now, firstly, I will discuss about the very short answer type question. So, very short answer questions. Very short answer question. Now, first is state Hooke's law of elasticity. So, student, what is Hooke's law of elasticity? We have discussed in the previous slide about the Hooke's law of elasticity. What is Hooke's law of elasticity? That within the elastic limit, the stress is proportional to strain. On removing a sign of proportionality, a constant will become which is known as E. E is the modulus of elasticity. So the value of E is stress upon strain. Or SI unit of modulus of elasticity, Newton per meter square, and dimensional formula is ml minus 1 t minus 2, and CGS unit is dyne per centimeter square. So first question is clear, the modulus of elasticity. Okay, we have discussed this question. So this is modulus of elasticity. Now next question is question number 2 is state the unit and dimension of stress. State the unit and dimension of stress. State the unit and dimension of stress. So we have discussed this topic also in our previous slides. Thus, stress is equal to force upon area. So its unit will be Newton per meter square. So unit will be Newton per meter square, and dimensional formula of force is mlt minus 2, and the dimensional formula of A is L2. So the dimension formula will be ml minus 1 t minus 2. All of these questions are your previous year question. Now question third is state the unit and dimensions. State the unit and dimensions of modulus of elasticity. Modulus of elasticity. So 1 minute, huh? We can write Newton per meter square also as Pascal. Okay, because Pascal pressure has same unit Newton per meter square. So modulus of elasticity is stress upon strain. We have discussed in our previous slide also the stress upon strain. So strain does not contain any unit. So all the unit of strain is equal to the modulus of all the units and dimension of stress is equal to the modulus of elasticity. So it has same unit Newton per meter square or Pascal, and the dimension is also same as ml minus 1 t minus 2. Okay, now next very short answer question is state the unit and dimension of modulus of rigidity. State the unit and dimension of modulus of dimension of modulus of rigidity. State and dimension of modulus of rigidity. Modulus of rigidity is also a modulus of elasticity, and I have said you in the previous slide that all modulus of elasticity have same unit and same dimension. That means it have also Newton per meter square, and the dimensional formula is ml minus 1 t minus 2. So it has same dimensional formula ml minus 1 t minus 2, and its same unit is Newton per meter square or Pascal, or same CGS unit which is known as dyne per centimeter square. Dyne per centimeter square. Now the last very short answer type question is state the example of state the example of perfectly elastic and plastic body. Perfectly elastic and plastic body. Perfectly elastic and perfectly plastic body is there. Okay, so the example of perfectly elastic body is quartz fiber, and the example of plastic body are clay, dove, etc. Now next is long answer type question. Short answer type, long answer type question. There is no short answer type question in this. All are long answer type question. So long answer type question. So long answer type question. First is define modulus of elasticity. Define modulus of elasticity, comma stress, comma strain, and Poisson's ratio. And Poisson's ratio. Poisson ratio. So, student, what is modulus of elasticity? We have discussed in the previous slide that modulus of elasticity is defined as the ratio of stress to the strain. So, modulus of elasticity is clear, which come from Hooke's law that within the elastic limit, the stress is proportional to strain. This is known as the modulus of elasticity. Modulus of elasticity is defined as the ratio of the stress to the strain. Next, in if this question come in a short marks question, so you will define only stress. Okay, you will define only stress, that stress is equal to force upon area. But if this question come as a long answer type question, uh, so you have to write all about it, that what is tensile stress, what is compressible stress, what is hydrostatic stress, what is tangential stress. Second, same you have to define strain, the change in dimension upon original dimension. Now the change, the type of strain. And the last one is our Poisson's ratio. What is Poisson ratio now? Last question is define Poisson ratio. So Poisson ratio is that within the elastic limit, the value of lateral strain to the longitudinal strain is known as the Poisson ratio. It has no unit and dimension. Now, next question is next long answer question is define strain energy, strain energy, and derive equation for C, and derive equation for same. So, student, what is the strain energy? Strain energy nothing but same as the elastic potential energy. Elastic potential energy is also known as strain energy. Okay. So I have described it about in a detail, that what is elastic potential energy? The energy stored during the stretching of wire is known as the elastic potential energy. And the derivation of elastic potential energy is here, that we prove the formula, that in an elastic potential energy per unit volume is defined as the half stress into strain. Okay. Now the last one is define Young's modulus, bulk modulus, and shear modulus. Young's modulus, bulk modulus, and shear modulus. And shear modulus. So, student, I also describe all these types of modulus, Young's modulus, bulk modulus, and shear modulus. That Young's modulus of elasticity is defined as the longitudinal stress upon longitudinal strain. Bulk modulus of elasticity is defined as the normal stress to the volumetric strain, and the last one is modulus of rigidity is F upon A upon theta. Okay, so that's all for today. In next class, I will discuss some more question about it.